Okay, so this is our first virtual problem solving session. We're running it on Tuesday because Monday was a holiday, but it's going to be about the same time every Monday instead. And the requests I received on Blackboard were to look at homework 1, problem 2, parts 2 and 3, and then homework 1, problem 3. And these are all kind of the same type of problem, so I started out by writing out a general approach for you all that I'll talk about and how problems 2 and 3 are different from each other. And I'll work through problem 2 in a lot of detail, and then I'll go a bit more lightly over problem 3. That way there's still a little bit for you all to figure out on your own. So, the problems that were requested are these problems about the fundamental existence and uniqueness theorem for initial value problems. And so our general approach for this type of problem is going to be, we're asked to find an interval where the solution to an ODE is guaranteed to exist. So in order to find that interval, what we do is we identify discontinuities, things that are sort of going to violate this theorem that tells us the interval is going to exist. And then we're going to define all possible intervals that exclude those discontinuities, because those things make the theorem no longer apply, so we're not guaranteed to have a solution. Then once we have all these candidate intervals, we're just going to choose the one that includes the initial condition from our initial value problem. So we want to make sure to pick a region of the X space where it's actually relevant to the problem we were asked to solve. The way that problems 2 and 3 differ from each other is just that problem 2 is kind of like the introduction to this idea. So you're given this nice paragraph that has some conditions to check for identifying discontinuities and making sure you get the right interval. And then once you move on to problem 3, you don't follow those rules necessarily. You just go ahead and look for those discontinuities yourself, and it's going to end up being that you just check for dividing by 0. So going through these kind of individually, for problem 2, first I want to make sure that you all know that you are supposed to refer back up to the top for your ODE and initial condition for the initial value problem. And also in this last part, you are supposed to refer back to the solution. So I think these black lines right here made people think that it was kind of a break in the problem and this was something new, but that is just calling out the reference that you need to solve the problem. It is all still part of the same problem that uses the same equations. So our initial value problem is 2xy prime is equal to 8y, and y of minus 1 is equal to 1. And we're given this sort of intimidating paragraph about how to check the fundamental existence uniqueness theorem. So I'm going to read through it so that you can kind of get a feel for what you're supposed to get out of the paragraph. So we're told, given an initial value problem, a1 y prime plus a0 y equal to g, with y of x0 equals y0, we're supposed to assume some stuff. And before we get to that point, I just want to make this equation right here kind of make sense for our problem. So we're supposed to have something that looks like this. And instead we have this given to us. So all I'm going to do is subtract this 8y from the right side and move it over to the left. So I'll have 2xy prime minus 8y is equal to 0 left over on the right. And then I don't have to do anything to my initial condition. It already looks like that. But hopefully now you can see that sort of 2x and a1 are the same thing, minus 8 and a0 are the same thing, minus 1 and x0 are the same thing, and 1 and y0 are the same thing. Oh, I skipped one. I skipped it because it's 0. 0 and g of x are the same thing. So now if this paragraph tells us anything about A1, A0, G, X0, and Y0, now we know how our problem is related. So in order to use this theorem, we need to assume that A1, A0, and G are continuous. That means that a condition for us to use the theorem is that A1, A0, and G are continuous. Or we need to check for all the places where that's not true because we can't consider those points. But A1 equal 2x, A0 equal minus 8, and G equals 0 are all continuous everywhere. You could graph those functions really easily. You wouldn't have any weird jumps or gaps in your function. So this interval a less than x less than b with a less than x0 less than b, we don't really know anything about it at this point because a1, a0, and g are continuous everywhere. So as far as we know, we could have minus infinity less than x less than infinity. Nothing's gone wrong for us yet. And I'm going to come back to this part in a little bit after we finish going through all the conditions. So the next kind of condition we're given is that we also need a1 not equal to 0 for everything in this interval. So a1 is 2x, and that's going to be 0 when we plug in x equals 0. That means that I need to exclude x equals 0 from my interval in order to use this theorem. So some intervals that are going to exclude 0 are going to be from negative infinity to 0 or from 0 to infinity. Looking at it like this on a number line, I wanted to give myself lots of space, but I probably overdid it and gave myself too much space. That's fine. So on this number line of x from minus infinity to infinity, this value x equals 0 is just kind of no good for us. We can't include that value when we're constructing intervals for this theorem. But if we wanted to, we could think about minus infinity to 0, or we could think about 0 to infinity. Those are still valid intervals for us. And then we're told there exists a unique solution on the interval a less than x less than b. So in these examples, a and b are going to be those bounds of interval that I've been looking at where we avoid the discontinuities. And now we just have to find a way to choose between these two because we can only put one answer in our web work. And so we're going to go back to this thing that I glossed over earlier. We need to have a less than x0 less than b. And for us, x0 is this minus 1. So we need minus 1 to be between a and b. And that really just means that we need x0 equal to minus 1 to be in the interval. So that's going to be like right here, minus 1. And so that tells me that the interval I need to pick is between minus infinity and 0. Or the a and b I have to pick is minus infinity less than x less than 0. So my answer is going to be that minus inf less than x less than 0. And when I put that in, it is correct. If you're getting like a yellow warning sign, make sure you're using this inequality notation, not interval notation. And then you should be good. Let's see, is there anything I skipped talking about here? So just to show you kind of the way this broke down, part 1 was kind of us doing this up to here. And then part 2 of actually picking the intervals that avoid those discontinuities was right here. And then part 3 of choosing the one that includes our initial condition was right here. And then just remember that we find these intervals by finding where these functions of x are continuous. So we find values of x to exclude, or we're building intervals that are in terms of x. And so when you get to this last point of choosing your interval, you need to make sure to choose based on the initial x value, x0, not the initial y value, y0. So you're going to go off of the thing that's inside parentheses that sort of tells us when our solution starts, not necessarily the value it starts at. This third part right here tells us sometimes the fundamental theorem is kind of like too conservative. It tells us the bare minimum interval where you're guaranteed to get a solution, but you could have a solution over a larger interval. So going back to part 1 of this problem, what's the actual interval where the unique solution exists? So we go back up to, in part 1, we were told the solution is y equal to c x to the r, and y'all would have gone ahead and found what c and r are. I guess I can just, here, don't look at the answer down there. We're just stealing this part and pretending we did it. So in my web work problem, C was 1 and R was 4. I don't know how I made that appear or how to make it go away better than that. Okay. So we want to check what's the actual interval where this solution exists. And y equal to x to the 4th exists everywhere. You could go ahead and draw that from minus infinity to infinity and not run into any problems. So the actual interval of existence is minus infinity to infinity. Oh, I keep wanting to do that interval notation. And that is the correct answer. I should have stopped showing correct answers before I did that. And so just the way you do that third part is go ahead and check your solution, see when it exists, but this one exists everywhere and it's unique everywhere. It only takes on one value for any x you plug in. So it's got a bigger interval of existence than you sort of guess following the rules of the theorem, is all you're supposed to get from that third part. So then problem 3 is just a little bit different. We're given a new ODE. Oh, I don't know what I'm doing to make that go back, sorry. Like this, and the paragraph that you had in the previous problem isn't there anymore, but you're still doing the exact same thing. You're finding the interval of existence for all of these different sets of initial conditions. And so that means that you're going to have to check when the functions are continuous. that means don't divide by 0. I underlined the 3 functions, but sort of for yourselves, go ahead and see how these relate to A1, A0, and G. And then this leading function right here, you also check when it's non-zero, but since it's just the constant 1 for me, I wouldn't have to worry about it. And I think that's true for everyone. So you really are just checking dividing by 0. You should get 3 x values to exclude. If you only get 2, give it another think and try to find out where that third one is supposed to come from. And then I'm going to recommend that you all do like I did with that number line. So go ahead and put the discontinuities, the place where you divide by 0, wherever they end up on your number line, like that. Just suppose those are 3 different numbers that I found by checking continuity of the terms in my ODE. And then once you have that, check where is x0 on your number line. You're going to get that from these initial conditions. Make sure you're checking the x value, not the y value. And then you're going to go ahead and pick the biggest interval that includes x0 and excludes discontinuities. So, for example, if that was my x0 right there, then the interval I would pick would be this one that's between suppose this was like 1 and 3, I would say 1 less than x less than 3, for example. I actually just want to make those numbers go away, but I'll leave the picture there because I think it might help. So I used star to indicate x0, and I used these little red squiggles to indicate the discontinuities. And then, oh, that's okay, we're almost done. My interval was that thing. So I'm hoping this picture kind of helps if you're more of a visual person to see what I mean by these steps. It is exactly the same steps we took here. So you're gonna check for these functions now, where are the discontinuities, exclude those points. You're gonna have 3, so there's more of them. The intervals are a little bit different. And then you're gonna pick the interval that includes your initial condition, sort of the same way I did here. So I hope that that's sort of enough of a step-by-step or hints to get you started on it without actually working through the problem for you, because I worked through it there and I don't really want to do 2/3 of the homework in a video. Yeah, so nobody came here. If you all ever come to the virtual problem solving session, I will go ahead and ask if there are questions and answer them. But for now, I'm just going to stop this recording and get it posted for anyone who couldn't join live.